Cette conférence va maintenant être enregistrée.
It's time to start now. So welcome everybody. Assalamu alaikum. So now I will present you this second session on laboratory design, and we'll clearly focus on the height control measures. So these measures are the measures that may be needed depending on the risk assessment for some specific situations where we consider that the core requirements, so the requirements that are mandatory, that should be in all labs, that those core requirements are not enough to ensure a sufficient level of biosafety. So if the core requirements are not enough, we might need some specific height control measures. And these control measures, they could also relate to different aspects, such as good work practices and procedures, competences and training, also to personal protective equipment, like respiratory protection that we usually don't wear, but in some cases we might need to wear it. Also laboratory equipment and management, also to decontamination, we might require some more specific decontamination technique, and also waste management, we might require some higher level autoclaves, for instance, and so on. And it can also relate to occupational health. For instance, vaccination may be a height control measure in some cases where we judge that otherwise the people will not be protected enough. And also, finally, laboratory design. So again, like for core requirements, laboratory design features are only one part of the possible height control measures. So if we think about having more stringent height control measures in laboratory design, we may think of different main options. The first one would be to add some additional separation means, some more containment. For that, we could simply apply the segregation rules in a more strict way. We could also have more sophisticated control access systems like electronic control access system. We could also improve the room integrity, so have a higher level of ceilings, have some level of air tightness of the lab. We could have an entry room before entering the lab. And we could also use protective cabinets like biosafety cabinets. And we could use some closed systems and equipment safety device, like for instance, the safety buckets that could be used for centrifuging. Other ways to have height control measures could be to work on the air control means. So we could provide a directional airflow, an airflow that goes from outside to inside to keep everything inside and thus create a negative pressure. We could also use some filters, mainly HEPA filters. And then we could also work on more developed decontamination means, like airborne decontamination systems, like VHP treatment, like an increased way to decontaminate waste, and also effluent decontamination systems. I will not cover this in these topics in this webinar. Why? Because it's quite distinct from the rest, and also it was covered by a webinar provided last year, and you can still find this webinar on the PEPSA YouTube channel. Anyways, you don't have to take all those height control measures as a whole. You need to define individual control measures on the basis of the risk assessment. You need to see where there is a weakness in the protection, and to cover that weakness, you need to define some height control measures. So how to select those height control measures? So according to WHO, the most appropriate height control measures will vary considerably depending on the biological agent being handled, but also on the laboratory activities being performed and on potential transmission routes. So again, it refers to biological risk assessment. And clearly, additional control measures need to be strictly based on risk assessment. And remember that risk assessment is not only looking at the agent and the activity, but also at the local context, including the availability of treatment, of measures and so on. I will take an example to illustrate this selection of height control measures. It's about the handling of concentrated culture of a quite high pathogen, which is transmissible by air. And during the activities of handling, there is some risk of aerosol generation, either during normal handling or in case of an accidental spill. And during the risk assessment, we consider that the risk is not acceptable if we only apply the core requirements. And so then we need to think about, more, and we need to think about some additional measures. And since it's transmitted by air and the weakness is probably at that level, we think about air control measures that would reduce that risk, or possibly respiratory personal protective equipment, such as masks, for instance. But of course, in that case, we don't need to consider an effluent decontamination system. Why? Especially if the agent does not survive in the environment. So we need to focus on the reason why the risk is not acceptable. And then, of course, we need, if we think about air control measures, we need to define which one we would need for personal protection, but also for the protection of the community or the environment. So when selecting those height control measures, we need to consider that all those measures have their own advantages and also disadvantages. There are pros and then there are cons. So for each one that we would need to put in place, we need to evaluate the most appropriate way to do things to bring risk to an acceptable level. If we keep with that example and want to control the risk of personal exposure, we could think first about biosafety cabinets. But in that case, which class would we need? Which type of biosafety cabinet? What would be their efficacy to reduce the risk? What would also be their cost? Also, do we have people or companies around that could do the checking and maintenance means that are needed? Is it sufficient to also control the risk of external release and dissemination? So when we think about risk control measures, we need to think about all those aspects. And then if the answer to that is no, there is no availability and so on, it's not sufficient, what could be possible alternatives? Like, is it possible to use closed systems? Is it possible to use personal protective equipment? And also compare their pros and cons. And then if we want to control the risk of release and dissemination into the community, we also need to look at the control measures. Are they sufficient to prevent that risk? Do we need to put some additional ones? And then which ones? Negative pressure, for instance, or HEPA filtration. And for that also, we need to look at the efficacy of the measure, but also the cost and benefits of all the possible options. I will give you more detail about that a little bit later. Still for the selection, when we select the most effective, we need to consider a number of things, but also the local needs and also the local availability, not only of the equipment, but also of the skills that are needed to maintain the equipment, for instance. So for that, we need to think in really pragmatic terms. We need to think local. We need to consider sustainability aspects. This means that one lab may end up with measures that are different from another lab, even if the activities are more or less similar, just because the local availability of maintenance means, for instance, is not the same. So if we keep that example, we need to look at the local availability of the class 2 biosafety cabinets, for instance, and also if there's local capacity to check and maintain those biosafety cabinets. If not, we might need to consider another type of cabinet, like class 1, for instance. With respect to air control measures, are there some local suppliers and installers, but who could also be able to ensure preventive maintenance or urgent repair? If all your system is based on a sophisticated air conditioning, and that in case of breakdown, you cannot repair it, your activity might be compromised. And then again, if if you don't find suitable solutions there, you might need to find something else, perhaps more simple, which is not as classical, but which should be more sustainable and really reduce the risk to an acceptable level. Before going further, I want to remind you about one concept which is used in laboratory design. It's a concept of primary and secondary containment. You see on this picture here, you see on the left-hand side, you see some tubes which contain biological agent. Then you see two people working in the lab. The first one working in what is a biosafety cabinet and the other one on the bench. Primary containment is actually the separation between the biological agent and the people in the lab and the lab itself. So that's really primary containment. So primary containment will protect, will avoid the exposure of the people in the lab, but also avoid the contamination of the lab. You also see outside of the lab the population and the environment, with in this case some livestock, some cows. Secondary containment will be the barrier that separates the activities of the lab from the outside, from the environment and the community. So the walls and windows and doors of the lab itself, the negative pressure and so on, that's secondary containment. Then when selecting the measures, if we need to decide about primary and secondary containment, we should first consider that in general, primary containment is more effective than secondary containment, because it allows reducing the risk for the personnel. It will reduce the risk of personnel exposure and thus infection, but it will also reduce the risk of having the laboratory contaminated. And if your laboratory is not contaminated, first, it's better for your experiments or your diagnostic activities, but you will also indirectly limit the risk of releasing the contamination to the outside. Also, primary containment is not just like Biosafety Cabinet or some device. It's also appropriate good practices that will really reinforce the effect of the equipment, and also PPE if needed. One thing we need to remember also, and that's quite general, is that containment is much more cost effective at a small scale. A biosafety cabinet, for instance, they treat air. There is an airflow, there is a HEPA filter, and because of the small volume of air, because of the small dimensions of the HEPA filters, it's much less costly than having the same type of airflow or a filter at the level of the whole room, for instance. So working at small scale is almost always more cost effective than at a larger scale. Then, even if primary containment is more effective, in some cases, still on the basis of our risk assessment, you might consider that it's not enough, and yet that you still need some secondary containment measures. So this is the end of this introduction. So I would ask Zova if she could summarize this first part, please.
Yes, thank you, Philip.
Thank you, Zova.
बायोसेफ्टी के मकासद के लिए लेबॉर्ट्री के डिज़ाइन में पहले नशिस्त में हमने बुनियादी ज़रूरियात पे बात की थी। आज की नशिस्त में हम अज़ाफ़ी कंट्रोल के इक़दाम पे बात करेंगे। अज़ाफ़ी कंट्रोल के इक़दाम का मतलब क्या है? खतरे को कंट्रोल करने के लिए ऐसे इक़दाम हैं जिनका लेबॉर्ट्री की सहूलत में सिर्फ इस वक्त लागू किया जाता है अगर खतरे की तशख़ीस से ज़ाहिर होता है कि खतरे को सिर्फ बुनियादी ज़रूरियात के साथ काबिल कबूल सतह पर नहीं लाया जा सकता। बुनियादी ज़रूरियात के तौर पे मुख्तलिफ पहलू हो सकते हैं, जैसे कि हमने पहले नशिस्त में इस पर बात की थी कि अच्छे काम के तरीक़ाकार जिसको हम GMPPs कहते हैं। इसके अलावा PPE ज़ाती हिफाजती साजो सामान, पेशा वराना सेहत اور ان میں سے ایک پہلو آتا ہے لیبارٹری ڈیزائن یا لیبارٹری کی ساخت کی خصوصیات پہ. اس میں پہلی سیریز میں لیبارٹری لیب کے ڈیزائن سے میں استعمال ہونے والے اضافی کنٹرول کے اقدامات جن کا تعلق اضافی علیحدگی یا کنٹینمنٹ کا لفظ استعمال کریں گے ہم اس کے لیے اس پریزنٹیشن میں. وہ کچھ مدرجہ ذیل ہیں. ان کے علاوہ بھی کچھ ہم انفرادی کنٹرول کے اقدامات کو خطرے کی تشخیص کی بنیاد پر فیصلہ کرنے اور منتخب کرنے کی ضرورت ہے. اس کا مطلب ہے کہ ہم پہلے اپنے خطرے کی تشخیص کے حساب سے اس بات کا اندازہ لگائیں گے کہ ہمیں بنیادی ضروریات ہمارے لیے کافی ہیں یا ہمیں کچھ اضافی اقدامات کی بھی ضرورت ہو سکتی ہے. یہ اس پریزنٹیشن میں ہم ان چیزوں کو آگے وضاحت مزید کریں گے. اگر اس کی اضافی کنٹرول کے اقدامات کے انتخاب پہ بات کریں، اضافی خطرے کی تشخیص کی بنیاد پر اضافی کنٹرول کے اقدامات کی وضاحت کرنے کی ضرورت ہوتی ہے. مثال کے طور پر اگر آپ کسی لیب میں ایک بہت کنسنٹریٹڈ کلچر کے ساتھ کام کر رہے ہیں جس کا ہوا کے ذریعے منتقل ہونے کا خدشہ ہے اور اس کے کام کے دوران یا حادثاتی طور پر اس کے پھیلنے کی صورت میں ایروسول پیدا ہو سکتے ہیں، تو اس صورتحال میں صرف بنیادی ضروریات کو لاگو کر کے خطرے کو قابل قبول حد تک قابو میں نہیں لایا جا سکتا. اس کیس میں ہم یہ کہیں گے کہ کچھ ہوا پر قابو پانے کے اقدامات اور کچھ اضافی پی پی کو لاگو کرنے کی ضرورت ہوگی. اور ذاتی حفاظتی اور لیب کے باہر، جس کو ہم کہتے ہیں کہ لیب کے باہر کی کمیونٹی کے تحفظ کے لیے کون سے فضائی کنٹرول کے اقدامات کی ضرورت ہو سکتی ہے، یہ ہمیں خود اندازہ کرنا ہے اپنے خطرے کی تشخیص کی بنیاد پر. اضافی کنٹرول کے اقدامات کے اپنے کچھ فوائد اور نقصانات ہیں. اس میں اگر خطرے کو قابل قبول سطح پر لانے کے لیے انتہائی موزوں اقدامات کا اندازہ لگانے کی ضرورت ہوتی ہے. مثال کے طور پہ جو ہم نے پچھلی سلائیڈ میں ایک مثال دی ہے جس میں ایروسول پیدا ہونے کا خطرہ ہے، اس میں ہم بایوسیفٹی کیبنٹ اگر استعمال کرنا چاہیں تو ہمیں اس بات کا اندازہ لگانے کی بہت زیادہ ضرورت ہے کہ کون سی بایوسیفٹی کیبنٹ کا استعمال کریں گے، اس کی کون سی کلاس ہوگی، اس کی کیا افادیت ہے، کتنی لاگت آئے گی، اور جانچ کے لیے اور دیکھ بھال کے لیے مقامی ہماری سطح پر اس کی سہولت دستیاب ہے یا نہیں ہے. اور اسی طرح بیرونی رہائی اور پھیلاؤ کے لیے جراثیم کے بیرونی رہائی اور پھیلاؤ کے خطرے کو بھی کنٹرول کرنے کے لیے کیا یہ بایوسیفٹی کیبنٹ کافی ہے. اس کے علاوہ متبادل راستے کون سے ہو سکتے ہیں، ہمیں اس بات کو بھی مد نظر رکھنے کی بہت ضرورت ہے. جراثیم کے بیرونی پھیلاؤ، رہائی اور پھیلاؤ کے خطرے کو بھی کنٹرول کرنے کے لیے کون سے اضافی اقدامات کی ضرورت ہوتی ہے، جیسے کہ مثال کے طور پر سلائیڈ میں لکھا ہوا ہے نیگیٹو پریشر، جس کو ہم منفی دباؤ کہیں گے. ہیپا فلٹرز اگر ہمیں استعمال کرنے ہیں تو ان کی قیمت کیا ہے، ان کی ایفیکیسی یا ان کی فوائد کتنے ہیں، اور ان ساری چیزوں کو ہمیں مد نظر رکھنے کی بہت ضرورت ہوتی ہے. عملی لحاظ سے سوچیں، مقامی پائیداری کے پہلوؤں پر غور کریں، یہ بہت ضروری ہے. بایوسیفٹی کیبنٹ کی ہی اگر ہم مثال کو آگے بڑھائیں تو کیا کلاس 2 بایوسیفٹی کیبنٹ اگر ہم استعمال کرنے کے لیے کہتے ہیں تو اس بایوسیفٹی کیبنٹ کی مقامی دستیابی، جانچ اور دیکھ بھال کی صلاحیت موجود ہے یا نہیں ہے. اور اس کے علاوہ فضائی کنٹرول کے اقدامات جسے ہم اس کے لیے بھی ہم کہتے ہیں کہ ہمیں مقامی سپلائر یا جو انسٹال کرنے والے ہیں اور احتیاطی دیکھ بھال اور فوری مرمت کو یقینی بنانے کی حقیقی صلاحیتوں کے حوالے سے بھی ہمیں ان چیزوں کو بھی مد نظر رکھنا پڑے گا. کیا خطرے کو قابل قبول سطح پر تک لانے کے لیے کچھ متبادل راستے اختیار کیے جا سکتے ہیں؟ اگر ہم بہت مہنگی اور اس طرح کی چیزوں پر نہیں جانا چاہ رہے تو کچھ متبادل راستے جو زیادہ مؤثر اور زیادہ پائیدار ہوں. اس تصویر میں آپ دیکھیں گے علیحدگی کا مطلب، اس میں اگر بایوسیفٹی کے لحاظ سے ہم علیحدگی کی بات کریں تو اس کا مطلب ہے پرائمری اور سیکنڈری کنٹینمنٹ. پرائمری میں مثال کے طور پر حیاتیاتی مواد یا جو جراثیم جس کے ساتھ ہم کام کر رہے ہیں، لیبارٹری کے اندر کام کرنے والے کارکنوں کے درمیان علیحدگی کی بات ہوتی ہے. और जब हम सेकेंडरी कंटेनमेंट की बात करते हैं उसका मतलब ये होता है कि जो लैब की सरगर्मियां हो रही हैं उनको बाहर की सरगर्मियों से अलग करें। बाहर का मतलब बाहर की आबादी से और बाहर के माहौलियात से। इनफरादी खतरे से दो चार होने से बचाने के लिए किस तरह के कंट्रोल की ज़रूरत होगी। अब हम इनफरादी और फिर बैरूनी फैलाव दोनों इस स्लाइड में हम दोनों पे बात करेंगे। इनफरादी के लिए अगर हम कहते हैं कि इसमें मिसाल है बंद सिस्टम्स का इस्तेमाल करें। बहुत सारी लेबॉर्ट्री की टेस्टिंग के लिए जो मौजूद होते हैं। बायोसेफ्टी कैबिनेट का इस्तेमाल करेंगे। सेंट्रीफ्यूज सेफ्टी बकेट्स होती हैं उनका इस्तेमाल करेंगे। और इसके अलावा इसके जो मुमकिन मुतबादल रास्ते हो सकते हैं उस पर हम कहते हैं कि बेहतर तरीके से अपनी सरगर्मियों को अंजाम देंगे जिसको हम GMPPs कहेंगे। उसके साथ PP का इस्तेमाल ये हमें इनफरादी खतरे से दो चार होने से बचाएगा। और अगर हम उसके अलावा हम बैरूनी फैलाव के खतरे पर काबू पाने की बात करते हैं तो सेकेंडरी कंटेनमेंट में से कुछ की ज़रूरत हमें हो सकती है। अगर GMPP और प्राइमरी कंटेनमेंट हमारा जो रिस्क है उसको कंट्रोल रिस्क को काबिल कबूल सतह पर कम करने के लिए नाकाफी हो तो उस केस में हम कहेंगे कि हम सेकेंडरी कंटेनमेंट वाली चीज जो इकदाम हैं उन पर गौर फिक्र करेंगे। इसमें कुछ मसाले हैं जैसे कि एंटी रूम का इस्तेमाल है, इसको हम आगे मजीद इसकी वजाहत करते हैं। या हेपा फिल्टर्स है, अंदरूनी हवा का दबाव है और इस तरह की कुछ मसाले हैं जो हम आगे इन पे मजीद बहस करेंगे। इसके अलावा प्राइमरी कंटेनमेंट आमतौर पर सेकेंडरी कंटेनमेंट से ज़्यादा मौसर साबित होती है। इससे खतरे को मुनासिब अच्छे तरीके से आसानी से मुनज़्ज़म किया जा सकता है और इस पे लागत भी कम आती है। और खतरे की तशखीस के इन्हिसार करते हुए प्राइमरी कंटेनमेंट के अलावा कुछ ऐसे वाक़यात केसेस होंगे जिसमें हम कहेंगे कि हमारे खतरे की तशखीस ये कहती है कि हमें प्राइमरी कंटेनमेंट के अलावा कुछ सानवी इक़दामात भी ज़रूरी हैं तो हमें करने चाहिए। तो हम फिर उन पे सेकेंडरी कंटेनमेंट के बारे में सोचेंगे। ओवर टू यू फिलिप।
Yes, thank you, Zorba. Now we'll start with the heat control measures that deal with the separation means. So with respect to room integrity, you have several levels. The normal level, according to core requirements, is to have the lab with the windows closed, for instance, and door closed when you work, but that's all. Then you could have an additional level if you have sealed windows. In that case, of course, you cannot open windows, for instance, when you don't work in the lab, but that's very easy to implement. But for that, you necessarily need some active ventilation and air conditioning. And then you can have another level, which is what we call clean room finishes. That means that most things are sealed, like sealed cable, duct, and so on, passages. And also you have finishes that are very easy to clean and disinfect and so on. So that's already a more sophisticated technical solution. And for that, you need specific skills to build that kind of facility. However, it's interesting not just for biosafety, but also to strongly limit contamination for biosafety and quality purpose together, I would say. And actually, since this is quite costly to have that, it's mostly reserved to specific activities that need a high level of quality control. Like, for instance, for vaccine production, for instance. Then the highest level of room integrity is air tightness. First thing is that 100% air tightness is not possible, and it's not even desirable because you could have many different drawbacks. Also, even to reach a very high degree of air tightness, it's very expensive because you need to pay a lot of attention and find technical solutions for everything. not just for the windows, doors, and so on, but also for each penetration in the lab. You need always to find something. But you might need a good level of air tightness if, for instance, you want to have decontamination done by a gaseous airborne system. If you want to regularly conduct some VHP treatment, for instance, in that case, you will need some high degree of air tightness just because you don't want to send that nasty chemical into the other rooms. So you might, in some case, if, for instance, the risk assessment shows and indicates that you need some frequent H2O2 VHP treatment, in that case, you will need some high degree of air tightness. Another way to increase separation is to have an anteroom. It's clearly not a core requirement, except in some regulations, but it is generally a good practice. For instance, for new labs, if you still have to build a lab, in that case, you could opt for that solution. Personally, I am really favorable to an anteroom. Why? Because it's a dedicated space for donning and doffing. So we will not do that either in the corridor or in the lab. You will do that in a specific place. It's also a dedicated space for hand washing. In that case, if you have a hand wash in your anteroom, people will not forget to wash hands. It's there in a well-located place, and it's very easy to do. It's also a good place for the storage of a number of things, including lab coats, including new ones, for instance, PPE, like gloves and so on, and also cleaning materials, pill kits, and first aid kits that should not be in the lab, but close by. If it's in the anteroom, it's very convenient, I would say. And then it's also a buffer zone which helps keeping good laboratory conditions. So in having an anteroom, it will be easier to keep a right temperature and humidity in the room. It will not be so easily influenced by the corridor, for instance. And so it's really a good way to favor good work practices and biosafety. So when it is possible, because you are thinking of new labs, you could really opt for such control measures. Also, I really believe that an anteroom is not necessarily a loss of space. If it's well organized, it will even allow to gain some space in the lab, in not having a number of things that should be close to the lab but not in the lab. This is an example of a very nice anteroom. It does not have to have the same level of finish, but you see a number of things there. First, you have a hand washing sink. In this case, it's not manually operated, and then everything that goes together. Some soap, tissue dispenser, and also a mirror, which could be helpful for gowning, for instance. Then you have the lab coats that are worn in the lab, so you have specific hooks for that. And then on the opposite wall, you can see in the corridor, you have some additional space for like gloves and so on, and also for lab coats or other clothes that are worn outside of the lab. And then finally, you have some storage, like for, in this case, for cleaning materials, pill kits, and so on. Also, an anteroom helps with respect to risk zonation. So you have the lab here with the high risk area, low risk area close to the entrance, and you have that anteroom, which is a buffer zone there. So it's clearly a neat separation between even the low risk area and the corridor. Another way to add separation means is to use biosafety cabinets or some other protective enclosure. So typically that's really primary containment. So biosafety cabinets are designed for the protection from infectious aerosols. They are clearly not a core requirement. Don't believe that each biosafety lab needs to have a biosafety cabinet. It's only if there is a risk of aerosol that could be infectious and that risk appears not acceptable in that lab. And also if there is no more efficient and more sustainable option, because in some case, if it's very limited work with some where there is some risk of infection through the airborne route, for that specific operation, it's sometimes much easier to wear a mask, for instance. So you see, you don't necessarily need to have such an equipment. So even if there were some other workshops on Biosafety cabinets, I will provide a few information on the main type of cabinets, because there are different types, classes 1, 2, 3, and they have very different characteristics. Don't forget also that there are some other protective enclosures, like chemical fume hoods. If you work on chemicals in that lab, chemicals from which there is some risk, and also some biological agent, but with a low risk, you can use the chemical fume hoods, which will protect you from both together. And then you could use some non-standard primary containment devices, and I will give you a good example of that a little bit later. Anyways, those containment devices, they have their value, but each one of them also have their constraints and some impact on laboratory design. For instance, the location of those equipment is something which is very important with respect to laboratory design. So the different types of biosafety cabinets. The most basic one is class 1 biosafety cabinet. So it's a closed enclosure. It's very simple in design. So you have a fan on the top of the cabinet, and that fan sucks the air from the lab. The air goes on the work table and then is filtered to a HEPA filter. So it is very interesting because it's very robust. It's a simple process. The airflow has one direction, it's very clear. And so because of that, there are not so many constraints with respect to location. You could put that in different places, even if they don't appear as the most favorable. Also, one thing is that you could connect the duct outside and connect it to the outside, so having a further duct there to go to outside of the lab. And in that case, you will ventilate the lab and you provoke a negative pressure very easily, actually. Class 2 biosafety cabinets, these are the ones that are the most used in many situations. Why? Because of one major advantage. They also offer some product protection in addition to personal protection. And there is also a fan on the top of the equipment. You see how it works on the right-hand side. And then the air is sucked under the work table, goes behind. Part of it is blown on the table, passing through a HEPA filter, so it's clean air. And the other part is blown to the outside, mostly, generally in the lab, to another HEPA filter. So its main value, as I said, is that it also provides some product protection. But the personal protection is not as good as with a class 1 biosafety cabinet. Why? Because that airflow is quite sensitive, and so you might have some disturbance here. And because of that, the location is much more important, but also work practices and so on. Also, it's a more sophisticated equipment, and so you will also need more checking and maintenance, and all that will make it more expensive to use in the long term. Class 3 biosafety cabinet, that's a glove box, completely closed with some gloves there. I will not talk more about that because it's almost never used in a biosafety lab. I spoke about location of a biosafety cabinet in the lab. Based on the principle of risk zonation, space zonation, the biosafety cabinet, which is the place where we handle hazardous materials with the risk of aerosols, should be in the high risk area. So it should be at the far end of the lab as opposed to the door. We also need to limit the impact of air movement and turbulence. And so it's at the end of the lab. We need to put it away from circulation routes, from places where people go in and out, for instance, also from blowing devices, like some air conditioning elements, or some heat sources. So in this case, on the drawing there, you see it's a perfect location. It's at the end of the lab, and people will not work there. If it was in the middle of the lab, that means that some people would go pass by, and especially with a class 2 biosafety cabinet, that is likely to disturb the airflow and thus to disturb the level of protection. So, Hvac, could you also please translate and summarize this part?
Yes, thank you, Philip. अब हम बात करेंगे अलहदगी के ज़राए पे मबनी इक़दामात की। इसमें सबसे पहले हम रूम की इंटेग्रिटी पे बात करते हैं। बंद खिड़कियों और इसके अलावा मोहर बंद खिड़कियां जिसको हम सील्ड विंडोज कहते हैं, उनके अलावा हम क्लीन रूम जो या क्लीन कमरे के इस्तेमाल पे आगे फर्दर मजीद जाके बात करेंगे, जिसकी अमल दरामदी के लिए मुख्तलिफ मखसूस किस्म की तकनीकी महारत दरकार होती है और ये बहुत महंगा है। और आखिर में हम बात करते हैं अगर मुकम्मल तौर पर हवा की तंगी की या एयर टाइटनेस की, ये 100% हवा की तंगी मुमकिन नहीं होती और अमूमी तौर पर ये बहुत महंगी है और इसकी ज़रूरत पेश नहीं आती लेबॉर्ट्री में। अब हम इस चीज़ पे बात करते हैं कि क्या हमें एंटी रूम की ज़रूरत होती है। तो इस पे हमारी बुनियादी ज़रूरियात में नहीं आता ये, लेकिन क्या आमतौर पर एंटी रूम का लेकिन फिर भी एंटी रूम का होना एक अच्छी प्रैक्टिस है, क्योंकि ये आपको पीपी को उतारने और पहनने के लिए एक मुनासिब जगह मुहैया करता है। और इसके अलावा लैब कोट या दूसरे पर्सनल प्रोटेक्टिव इक्विपमेंट पीपी जिसको कहते हैं रखने के लिए, सफाई के सामान के रखने के लिए स्पिल किट है, फर्स्ट एड किट है और दीगर डिस्पोजेबल सामान रखने के लिए भी एक मुफीद जगह है। और एक एंटी रूम अगर मुनज़्ज़म तरीके से इस्तेमाल किया जाए तो ये इंतहाई कारआमद साबित हो सकता है। जैसे कि इस तस्वीर में अगर आप देखें, आप देख सकते हैं कि बहुत से मुफीज अनासर जैसे कि हाथ धोने के लिए मुख्तलिफ किस्म के आलात, लैब कोट और मुख्तलिफ पीपी रखने के लिए जगह एक छोटी सी जगह पर मौसर तरीके से मुनज़्ज़म किया गया है। अब एंटी रूम का मकसद यहाँ पे अगर आप देखें तो जैसे कि रिस्क जोनेशन की बात की थी पिछली नशिस्त में, तो ये एंटी रूम एक बफर स्पेस या बफर की जगह पर प्रोवाइड करता है, जो कि जोनेशन के लिए, जो हम रिस्क जोनेशन की बात करते हैं, उसके लिए बहुत कारआमद साबित हो सकता है। आगे अब हम बात करते हैं बायोसेफ्टी कैबिनेट और इसके अलावा दीगर हिफाजती कैबिनेट्स या आलात की। बायोसेफ्टी कैबिनेट फिजा में मौजूद जरासीम की मुंतकली से बचाता है और बायोसेफ्टी कैबिनेट एक बुनियादी ज़रूरत नहीं है। ये बात यहाँ काबिल गौर है कि बायोसेफ्टी कैबिनेट बुनियादी ज़रूरियत में नहीं आता। इसकी ज़रूरत सिर्फ तब पैदा होती है जब मुमकिन खतरा लाहक हो और उसकी एरोसोल की पैदा होने का और इससे बचाव का कोई और दूसरा रास्ता मौजूद ना हो। बायोसेफ्टी कैबिनेट के अलावा और भी बहुत सारे बायोसेफ्टी कैबिनेट, जैसे हम अगली स्लाइड्स में उसकी मुख्तलिफ क्लासेस के बारे में बात करेंगे। इसके अलावा भी बहुत मुख्तलिफ किस्म के प्राइमरी कंटेनमेंट के आलात इस्तेमाल होते हैं। लैब के डिज़ाइन में सभी की अपनी अहमियत, अपने अपने असरात और अपने नुकसानात या रुकावटें हैं। इस प्रेजेंटेशन में हम, क्योंकि बायोसेफ्टी कैबिनेट के लिए एक अलग मोनोग्राफ है, तो इसमें हम बायोसेफ्टी कैबिनेट की मुख्तलिफ इक़सामात पर बहुत ज़्यादा बहस नहीं करेंगे। इसमें लैब के डिज़ाइन के हिसाब से जो इनके इक़दामात या जो चीज़ें काबिल गौर लाने वाली हैं, सिर्फ उसी पे बात करते हैं। क्लास 1 बायोसेफ्टी कैबिनेट है। क्लास 1 बायोसेफ्टी कैबिनेट आगे से ओपन होती है, हैपा फिल्टर मौजूद होता है इसमें, और इसमें लैब के डिज़ाइन पर अमल दरामद होने वाले असरात और रुकावटों में से ये ज़्यादा, हम कहते हैं कि ज़्यादा इसमें मजबूती वाला एक एलिमेंट होता है और लैब में इसकी जगह बहुत ज़्यादा सख्त ज़रूरियात नहीं है। लैब में किसी की भी जगह पर रखी जा सकती है और इसके अलावा बातनी हवाओं का दबाव, मनफी दबाव बनाने के लिए इसको आसानी से बाहर से मुंसलिक किया जा सकता है, लैब के बाहर से मुंसलिक किया जा सकता है। अगर हम क्लास 2 बायोसेफ्टी कैबिनेट की बात करते हैं, तो ये बायोसेफ्टी कैबिनेट भी आगे से ओपन होता है और इसमें 2 हैपा फिल्टर्स भी लगे होते हैं और इसकी देखभाल के लिए वसी पैमाने पे खसूसी तकनीकी महारत की ज़रूरत होती है, जो कि पाकिस्तान में इसकी दस्तयाबी इतनी नहीं है अवेलेबल। अमूमी तौर पर बाहर से इसको मुंसलिक नहीं किया जा सकता सवाए क्लास 2 बी बायोसेफ्टी कैबिनेट के, और लैब में इसको रखने की जगह बहुत गौर तलब होती है, क्योंकि इसकी वेंटिलेशन पर बहुत गहरे असरात मुरतब होते हैं। लैब में इसको ऐसी जगह पे रखें जिसमें आप हवा का वेंटिलेशन का दबाव और इस तरह की चीज़ों को उससे पहले मद्देनजर रख लें। क्लास 3 बायोसेफ्टी कैबिनेट है, ये अमूमी तौर पर जैसे फिलिप ने बताया कि हमें इसकी ज़रूरत नहीं होती। ये बायोसेफ्टी कैबिनेट सामने से बंद होती है और हवा का बहाव बिल्कुल नहीं होता और इसमें भी HEPA फिल्टर्स लगे होते हैं। सो अगर हम हिफाजती तौर पर देखें तो ये बायोसेफ्टी कैबिनेट बहुत ज़्यादा मौजू है, लेकिन इसके इस्तेमाल के लिए बहुत ज़्यादा महारत की ज़रूरत होती है। बायोसेफ्टी कैबिनेट के लैब में जगह का तयन इस तरह से करना चाहिए कि जहां खतरनाक जरासीम के साथ हम काम कर रहे हैं उसको उस जगह पे रखें। मिसाल के तौर पे लैब के आखिर में या दरवाजे के बिल्कुल मुखालिसमत में। और हवा के बहाव ज्यादा नहीं होना चाहिए, खासतौर पर बायोसेफ्टी कैबिनेट क्लास 2 के लिए, और इसको कारकुनों की या लैब में काम करने वालों की आमदोरफ्त के रास्ते से दूर रखने की कोशिश करें। थैंक यू फिलिप, ओवर टू यू।
Thank you, Zora. So we'll now look at the height control measures that are based on so sorry. Do you see my screen?
Yes, Philippe, we do.
Okay, so as pointed out during session first, it's a quite tricky issue because on one hand, we need some ventilation for hygiene reasons, also to eliminate volatile substances that are likely to be used in the lab, and also to eliminate infectious aerosols that could be generated either in normal handling or in case of an incident. On the other hand, ventilation itself can be a source of problem. For instance, if you blow those volatile substances or infectious aerosol toward the people, in that case they might be exposed because of that or that ventilation. Also, if you extract the air and send it to the outside, it might be the cause of a release in the environment or in the population and dissemination in that environment or population. So that means that we need some ventilation, but we need to be very careful when we define the solutions that we want to put in place, because we want to do it so that it's well ventilated, but without exposing people either inside of the lab or outside of the lab. So, as you know, natural ventilation may be used in a lab as a very basic measure, but most of the time in biosafety lab, it's not something that should be done. Why? Because with natural ventilation, we have non-controlled airflows. So people could be exposed in case there would be an accidental aerosol, for instance. And also because of the impact of climate conditions, like air turbulence and so on the people, but also on product contamination and so on. So most of the time in a biosafety lab, you will need some active controlled ventilation. And from that point of view, there is one solution which is easy to implement and very efficient in providing ventilation, is to use an exhaust fan. That means a fan that takes the air from the lab and sends that air to the outside. And when we decide to use an exhaust fan, there are some rules that we should use. First, the fan has to be located close to the main source of the substance to eliminate. So if we have a good risk zonation with a high risk area at the end of the lab, that's clearly the place where the exhaust fan should be located. Also, if you take some air away from the lab, you will create a negative pressure in the lab. That means that some air needs to enter in that lab to compensate. Most of the time, with most labs, you don't have to worry about that because there are some leaks in different places, like under the door, next to close to the windows, and so on. But if you have a lab which is too airtight, in that case, you might need some ventilation slats. That means some grills that will allow the air in. if you put an exhaust fan, you create thus an inward airflow, which does a slightly negative pressure, which is generally a good measure, especially if there is some kind of spill and so on. You will not spread it immediately to the outside. But still, if you use an exhaust fan, you might still need to have some separate cooling system in order to ensure the right temperature in the lab. So I take the same example of that I use for space zonation. And in that case, we would clearly put the exhaust fan at the end of the lab. And that could be in the wall or in the ceiling of the lab, okay? And that exhaust fan, we suck the air from the lab. And so because of that, you create an airflow that goes from the clean place to the dirty place for the non-contaminated, low-risk place to the possibly contaminated, higher-risk place. So you clearly have a movement of air from clean to contaminated, from low risk to high risk. Most of the time, there is no problem to have that air that comes in there. If it's too airtight, as I said, you could have some ventilation slats. It could be in the door. It could be in some other place, like on the top, in the wall, or so. And so. That was for one room. You can also use the same principle if you have several rooms, like in this case. In this case, there is a low-risk lab, then an intermediate risk room, that could be the corridor, or a high-risk area. If you put the exhaust fan in the high-risk area, in that case, you will create a negative pressure and you will suck the air from the neighboring room. And so you could really have also an airflow from low-risk, from clean, to high-risk to dirty. So it's quite easy to manage. In this case, of course, you might need a fan which is more powerful in order to extract enough air to compensate for. With respect to finding the right solution based on your risk assessment and based on your need, I will present you an example that I really like very much. It's a situation that was that I discovered in a small hospital lab in Gilgit. So in that lab, they were working on TB, and they were mainly used smears from patients and diagnostic from those smears. So they were handling infected smears. Some were infected with TB, but some others with different type of other respiratory pathogens. There was no ventilation in the lab, and there was no window in the lab. Also, there was no biosafety cabinet in that lab. And not only that, but they had no money to purchase one and be able to maintain one. It's a quite remote area, and there is no real availability of good checking and maintenance. So what solution was it? Actually, it was a solution that was developed by a lab technician, one of the technicians who was working in that lab. And that guy, that guy designed and built a kind of enclosure like this. It looks like a biosafety cabinet, but of course it's not a biosafety cabinet. It's not certified as such. It has a very clean work area. It has a window to protect from splashes, for instance. And inside of that box, there is an exhaust fan that is connected to outside of the lab. And you put that cabinet at the end of the lab. And how does it work? That fan is sucking the air from the clean area of the lab to this place. And then that air that could be contaminated by the aerosol that could be created when handling is sent to the outside. So what does it do? Clearly, it offers protection for the people in the lab, better protection than before that. It also provides some ventilation of the lab, and also a good movement from clean to dirty, which also prevents the risk of contamination of the samples. So actually, that guy really thought about the situation and found a way that was accessible, that he could make himself, and that can be maintained easily. And the benefit is huge, and this is something which is sustainable. So I was really amazed to see that that guy had the idea to do that and did it so well, I would say. I think this example is good because even if your labs have a little bit more equipment and so on, it shows you that in thinking about the situation, in thinking really about the risk, what is the problem, and what are possible solutions, you could develop not necessarily the same thing, but smart solutions that work. Another possible way to increase to manage possible contamination through the air is to use filters, and the filters that are used for biosafety purposes are mainly HEPA filters. So they retain infectious particles in aerosols, and that could be infectious particles, but they will retain any type of aerosols, actually, of particles. Such filters are present in all types of biosafety cabinets, but they could also be installed in labs. And if we want, for instance, to protect the outside population, in that case, we could have HEPA filters on the exhaust of the lab. Sometimes they are also used on the air which is supplied in the lab to prevent contamination with external particles. That's for product protection, and it's used, for instance, in the pharmaceutical world for vaccine production or for different types of clean rooms. Do we need a HEPA filter? Clearly, again, it's not a core requirement. So we only need it if we consider that without a HEPA filter, the risk will not be acceptable. Still, we need to think about such a situation may generate some difficulties. There are some constraints and some limitations with HEPA filters. First, they will generate some pressure drop because the air goes through and it's filtering. It will be the fan that we'll need to use, for instance, will need to be more powerful for that. Also, if you install HEPA filters, they need to be installed in filter cases, but these need to be perfectly airtight, including the joints around it. If not, since the filter offers some resistance to the air will go around the filter, and so we will not filter the air. Also, you need to check the integrity of the filter. You need to check that there is no leak either in the filter or in the gaskets. And that's a specialized technical intervention. You will need to have probably a contractor to do that. Also, those filters are quite expensive, quite at installation, but also when you need to replace them. And if you are in a quite dusty environment, you will need to replace them quite often. And that means quite a lot of cost. Just to give you an indication, the third of the price of a Class 2 biosafety cabinet is the filters. So when you need to replace them, you have to pay for 1/3 of the price of the biosafety cabinet. So to me, HEPA filters only have to be installed for room ventilation for situations where the risk from aerosol release appears non-acceptable, and only if no efficient and more sustainable option is available. What are the possible options? The first one is to use a biosafety cabinet, which has its own HEPA filter, and to do everything that could generate an aerosol inside of the biosafety cabinet. So you will filter it at a small scale, but because of that, there will be no aerosol in your lab, and because of that, you will also protect the outside. That's a benefit of working at a small scale. You could also have some kind of that the exhaust of the air from your lab goes through a chimney and is delivered quite high, where there is dilution and where nobody outside could be exposed. And that, of course, depends on the resistance of the pathogen in the environment. Another way to manage ventilation and air conditioning is to use what engineers call Hvac systems. They combine both ventilation and air conditioning and offer quite a lot of control, but you see on the picture that they are quite big and complicated machines. So they need space, and they also need good engineering at the start and also good maintenance. So I would say that this should only be reserved to situations of high risk when it really appears as the best options, and where there also a way to keep the solution in place. So the constraints of such a system are high. It takes some space. They are complex and they take some space. And you see here it's on the top of a building. So it's also exposed to weather conditions. So it could be more easily damaged over time. Installation costs are very high, but also running costs because of the maintenance and also because of the cost of energy. It moves quite a lot of air. Also, and I would insist on this last bullet point, the capacity for good design, installation, and maintenance of such systems in Pakistan is quite low. The capacity is limited. Of course, such systems are installed in hotels and in some office buildings and so on. But the requirement for those systems for a hotel or a building service is much simpler. Also, in this case, I think it's also a good story. This system here is on the top of a BSL-3 lab for TB work, liquid culture of tuberculosis. And actually, from the start, that system never worked properly. And it was noisy, it was not maintaining the right temperature and so on. And so the people in the lab were not happy with that. And they also did not trust the system because it could not be fixed. And so the lab manager decided, we don't use it anymore. What did they do? They installed exhaust fans. And they also increased the work practices. They had biosafety cabinets. They had increased the work practice with a respiratory mask, even when using the biosafety cabinets. And so finally, that sophisticated equipment that they paid a lot of money for, they didn't use it. They adopted much simpler solutions. This again to illustrate that you don't necessarily need to have those fancy equipment, and that in some case, something which is much simpler can be much more efficient and can be used and can be sustainable. To finish this part, a word about the location and ventilation device and cooling systems. And I think that this is quite important. So there are two types of ventilation system, some that suck the air and some that blow the air, push the air. Exhaust fan, they suck the air, and also the exhaust wheel of a Hvac system. And so they create a directional airflow because they take the air from one place and send it to another place. But they do not create a real airflow disturbance. The airflow is quite direct, and those exhaust wheels of a HVAC system, for instance, they don't have an impact on a biosafety cabinet or on the performance of a biosafety cabinet. So you could easily place exhaust fans above a biosafety cabinet, right in front of a biosafety cabinet. There is absolutely no problem for that. And this is something that can be tested. There is absolutely no problem with this. On the other hand, if you have some air conditioning units and the air diffusing of a HVAC system or anything that blows the air, in that case, they generate positive pressure, but also they create some airflow disturbance. And because of that, air conditioning unit or air diffuser should never be put close to a biosafety cabinet. They should never be put in front of workers if they are likely to blow some hazardous products towards the worker. This is an example of a poor location of a cooling device. You see here a class 2 biosafety cabinet, and you see there the air supply grill of a air conditioning system and an additional split unit, probably because the air conditioning unit was not sufficient to provide fresh air. And when they tried to test, after a few years, to test the biosafety cabinet, it was not working properly because of the air disturbance. What did they have to do? They had to block the flaps there, so in order to send the air to the ceiling rather than towards the biosafety cabinet, and they had to cover part of the grill in order to deviate the airflow. But of course, then it worked. But of course, this would have been much better if it was on the opposite wall. And when you want to design a lab, it's better to think about that from the start when designing the lab. Okay, we'll put the air diffuser on the opposite area, so in the low risk area, for instance. So some conclusions, and I think that's these are the most important message from the 2 sessions of this workshop. The first thing is that according to WHO, core requirements, so that the things that we saw during the first session, are sufficient to control risk in most laboratories. Most of your labs, they should be okay with only using core requirements. Another important aspect is that good organization of the lab and location of the equipment, which are very simple to achieve, they are important and elements of risk control, and they are also not only easy but also sustainable. So in designing a lab, thinking about organization and location of equipment is really something which is extremely important. Then even depending on the risk assessment, some high control measures may be needed in situations to reduce the risk to an acceptable level. So I don't say that none of the lab needs some high control measures. In some case, depending on risk assessment, you might need some, not all of them, but some. But when you try to select those control measures, you need to really aware about their costs. Of course, it's quite clear what value they have, but they should also be selected with precaution, considering the costs, consider the constraints with respect to location, with respect to maintenance, for instance, and there's also the sustainability aspects. So when you think about height control measures, really think about the cost in general. Another principle that is very important to remind also is that it's more efficient and less expensive to apply height control measures at a small scale than at a large scale. So if you can have a biosafety cabinet, and that using a biosafety cabinet will prevent you from having sophisticated secondary containment measures, it will be better, because the biosafety cabinet will work on a small volume of air and will have good filters and so on. And so it will be much more effective and also less expensive than working at the level of the lab. And also, of course, in that case, you will have personal protection, which if you only work at the level of the lab, you will not have. It's also a reason to prefer a small lab rather than a large lab, especially for high-risk activities. And that's a reason for risk segregation. If you can do a high-risk activity in a small lab rather than in a big lab, not only you are likely to expose less people, but you will also be able to manage the risk in a more efficient and less expensive way. About primary containment. Primary containment, it's some equipment like a closed system, like biosafety cabinets. Good practices and PPE might be needed also, and good practices are needed with biosafety cabinets, for instance. But having all that, primary containment, good practice and PPE might be enough to avoid secondary containment measures. Again, there is a big advantage of working at a small scale. And then last, I think that there are 2 height control measures that are worth thinking about them, that can be easily be implemented to improve risk control. The first one is to use a well-designed and organized anteroom. And this is something that, at least for new labs, is quite easy to manage, and it will bring quite a lot of advantage. And this does not cost much more. I mean, it's an additional door and a few other things, but it's not something which is expensive or fancy to maintain. And then the second thing is that with respect to ventilation, using an exhaust fan is really a measure that has a lot of advantages to evacuate dirty air and manage airflows. You need to think about their position, and that has to be put in relation with the equipment and also with the risk zonation, with the space zonation of your lab. But this is also something which is quite easy to manage and really something which is sustainable. So thank you, and I will again ask Zuba if she can also summarize this part.
Yeah, thank you, Philip.
Thank you.
So, अब हम बात करेंगे एयर कंट्रोल के मुख्तलिफ तरीकों पे। इसकी हमने पहले के मरहले में इसकी वजाहत कर चुके हैं कि एयर कंट्रोल की अहमियत, एयर कंट्रोल और वेंटिलेशन की क्या अहमियत हो सकती है एक लैब के एनवायरनमेंट में, क्योंकि लैब्स में काम एक बंद एनवायरनमेंट में ही किया जाता है और लैब के वेंटिलेटेड होना चाहिए। इसके मुख्तलिफ फ़वाइद हैं, जैसे कि हिफ्ज़ान सेहत के वजूहात की बिना पर भी, और अगर हादसाती तौर पर एरोसोल का अखराज हो जाए तो इसका असर ख़त्म करने के लिए भी इसकी ज़रूरत होती है। दूसरी तरफ वेंटिलेशन एक जहरीली मादा, या हम कहते हैं कि हवा में जो मौजूद जरासीम है या एरोसोल हैं, उनके फैलाव का सबब भी बन सकता है। सो इसलिए लैब के डिज़ाइन के वक्त दोनों पहलुओं को मद्देनजर रखने की बहुत ज़रूरत है। वेंटिलेशन, कुदरती वेंटिलेशन जिसको बायोलॉजिकल रिस्क को कंट्रोल करने के लिए नाकाफ़ी है, इसलिए यहाँ एक कंट्रोल वेंटिलेशन सिस्टम की ज़रूरत होती है। इसको हम एग्जॉस्ट फैन के इस्तेमाल से बुनियादी और मौसर ऑप्शन है जिसके इस्तेमाल से हम इसको कर सकते हैं। जैसे एग्जॉस्ट फैन की जगह वहाँ बननी चाहिए जहाँ खतरनाक जरासीमों के अखराज का खतरा हो सकता है, और एग्जॉस्ट फैन हवा के दबाव बरकरार रखने में मदद करते हैं, और इसके अलावा अंदरूनी हवा का बहाव पैदा करते हैं। इस तस्वीर में अगर आप देखें तो आप एग्जॉस्ट फैन को एक लैब के ज़्यादा खतरनाक इलाके में लगा सकते हैं। इस तरह फैन आपके खतरे के पैदा होने वाली जगह से आलूदगी को ख़त्म करेगा, और इसके साथ साथ कम खतरे वाले इलाके की तरफ हवा का दबाव बनाए रखेगा। अगली तस्वीर में अगर आप देखें, इसी तरह मुख्तलिफ कमरों के दरमियान हवा के बहाव की नकलो हरकत पैदा की जा सकती है एग्जॉस्ट फैन के इस्तेमाल के साथ। आगे एक गिलगित की एक छोटी सी हॉस्पिटल की लैब की मिसाल है। उसमें असल में उस लैब में एक छोटी सी लैब है, उसमें टीबी के स्मेयर बनता है, और उसकी स्मेयर की हैंडलिंग होती है, और इन्फेक्टेड स्मेयर और दीगर जो खतरनाक केमिकल्स हैं वो इस्तेमाल होते हैं। उसमें कोई वेंटिलेशन का सिस्टम या हत्ता कि कोई खिड़की भी मौजूद नहीं थी, और बायोसेफ्टी कैबिनेट भी नहीं है, और ना ही लैब के पास कोई माली तौर पे कुछ ऐसी फंड्स मौजूद हैं जिससे उनको खरीदा जा सके। सो एक लैब टेक्नीशियन ने एक अपने तौर पे एक उसका हल तलाश किया, जिसमें इस टेक्नीशियन ने घर में खुद से एक बायोसेफ्टी कैबिनेट की तरह की एक आला बनाया, जिसको प्रोटेक्टिव इनक्लोजर की हैसियत से, और इसको खुद तैयार किया, और इसने एग्जॉस्ट फैन से उसमें एक एग्जॉस्ट फैन लगाया जिसका अखराज बाहर की तरफ था, और ये इनक्लोजर लैब के आखिर में या दरवाजे के बिल्कुल ऑपोजिट नस्ब किया गया, और नतीजे के तौर पर महदूद वसाइल में रहते हुए एक डेडिकेटेड बायोसेफ्टी कैबिनेट जैसा एक आला बना लिया, और जो कि जिसको हाई रिस्क के लिए बहुत मौजू था। हेपा फिल्टर्स, जिसको हम हाई एफिशिएंसी पार्टिकल एयर फिल्टर्स कहते हैं, ये हवा से फैलने वाली वबा से बचाता है, और ये सब टाइप की बायोसेफ्टी कैबिनेट में भी इस्तेमाल होता है। बाहर निकलने वाले हवा के रास्ते में लगाया जा सकता है, जिससे जो लैब के अंदर पैदा होने वाले जरासीम के ज़रात हैं उनकी रहाई को रोकने के लिए, और इसके अलावा इसको सप्लाई की हवा या लैब में अंदर दाखिल होने वाली हवा के रास्ते में भी लगाया जा सकता है, जिससे जो आलूदगी को लैब में अंदर आने से रोकेगी। क्या हमें बायोसेफ्टी कैबिनेट, क्या हमें हेपा फिल्टर्स की ज़रूरत है? हेपा फिल्टर्स की कुछ रुकावटें और कुछ हदूद हैं। ये कुछ महदूद हद तक प्रेशर को ड्रॉप पैदा करता है, और इसे एयर फिल्टर केस में बिल्कुल एयर टाइट गैस्केट में इंस्टॉल किया जाता है, और इस वजह से इसकी स्पेशलाइज्ड टेक्नीशियन से इसकी इसकी देखभाल बहुत लाजमी है। इसकी इंस्टॉलेशन और इसको तब्दील करने का अखराजात बहुत ज़्यादा हैं। सो इस वजह से सिर्फ इसको HEPA फिल्टर को तब इंस्टॉल किया जाता है जब एरोसोल का अखराज से पैदा होने वाला खतरा नाकाबिले कबूल हो। अगर ऐसा नहीं है तो इसके अलावा बहुत से मुतबादिल जरिए भी मौजूद हैं, जैसे कि बायोसेफ्टी कैबिनेट का इस्तेमाल या फिर एरोसोल को ऐसी जगह पर बाहर निकाला जाए जहां वो डाइल्यूट हो सके। अगली किस्म है HVAC, जिसको हम कहते हैं, ये हीटिंग वेंटिलेशन एयर कंडीशनिंग सिस्टम है। ये वेंटिलेशन और एयर कंडीशनिंग दोनों को यकजा करता है और इसके अलावा टेम्परेचर है, हवा में ह्यूमिडिटी या नमी है और कमरे के प्रेशर को भी कंट्रोल करता है। इसमें हम देखते हैं कि क्या हमें HVAC सिस्टम की ज़रूरत है। इसकी कुछ HVAC सिस्टम में हम करें तो आमतौर पर इंतहाई पेचीदा निज़ाम है और जिसमें जदीद इंजीनियरिंग और इसकी बाकायदा देखभाल की ज़रूरत होती है और बहुत ज़्यादा जगह दरकार होती है इस सिस्टम को लगाने के लिए और इंस्टॉलेशन और इसे चलाने के अखराजात भी बहुत ज़्यादा हैं। पाकिस्तान में इसकी देखभाल और डिज़ाइन की महदूद वसाइल मौजूद हैं। इसकी इंस्टॉलेशन सिर्फ तब ही कारआमद है जब माली और तकनीकी वसाइल आसानी से मौजूद हों, वरना आप इसके लिए किसी मुतबादिल रास्ते का इख्तियार करें। अगर हम वेंटिलेशन के आलात और कूलिंग सिस्टम की बात करें तो इसमें इसको ऐसी जगह पर लगाया जाता है, एग्जॉस्ट फैन की अगर सबसे पहले हम बात करते हैं तो इसकी जगह का तयन इस तरह करना चाहिए इसको ऐसी जगह पर लगाया जाए कि अंदरूनी हवा का दबाव पैदा करें और हवा के बहाव को में खलल ना करें। और इसके अलावा इसको बायोसेफ्टी कैबिनेट, अगर हम दूसरी तरफ उसके एयर कंडीशनिंग यूनिट की बात करते हैं तो उसमें ये हवा का मस्बत दबाव पैदा करता है, जिसकी वजह से हवा के बहाव में खराबी पैदा होती है ओवरऑल जो लैब के हवा के बहाव में। सो इसको ऐसी जगह नहीं लगाना चाहिए जहां काम करने वाले की तरफ खतरनाक ज़रात उड़ने का खतरा हो और बायोसेफ्टी कैबिनेट के करीब भी नहीं होना चाहिए इसको। इसके अलावा अगर हम इस तस्वीर में एक जो कूलिंग सिस्टम है या AC है उसका बिल्कुल नाकिस जगह पे जो लगाया हुआ है उसमें एक मिसाल देखते हैं कि इस तस्वीर में अगर आपको नजर आ रहा होगा कि HVAC सिस्टम के हवा की सप्लाई वाला ग्रिल जो है वो बिल्कुल बहुत करीब लगाया गया है और जिसकी वजह से हवा के बहाव में खराबी पेश आ सकती है और बायोसेफ्टी कैबिनेट बिल्कुल उसके सामने रखी हुई है और बायोसेफ्टी कैबिनेट की तरफ जाने वाली हवा के बहाव में खराबी पेश आएगी। और इसका आसान हल ये है कि सप्लाई का जो ग्रिल है उसमें जुज़वी तौर पर कोई रुकावट पैदा कर दी जाए। अब हम आज के इस मरहले में जिन चीज़ों पे हमने बहस की इसमें कुछ नताइज पे बात कर लेते हैं। सबसे पहले बुनियादी ज़रूरियात ही काफ़ी होती हैं किसी लैब में रिस्क को कंट्रोल करने के लिए और इसके अलावा लैब में आलात का सही जगह लगाना लाजमी है और इस वजह से रिस्क भी कंट्रोल किया जा सकता है। और इसके अलावा एक और बात है कि कुछ अजाफी इक़दामात की ज़रूरत पड़ सकती है जब खतरे को काबिल कबूल सतह पर लाना मुमकिन ना हो और हर आला इक़दाम की एक कीमत होती है और ऐसे इक़दामात उठाते वक्त हर पहलू को गौर से देखना चाहिए। इसके अलावा अगर हमने इस पे बात की थी कि बड़े पैमाने के मुकाबले में जो हम छोटे स्टेप्स लेंगे तो वो ज़्यादा कारआमद साबित होंगे जब हम अजाफी बायोसेफ्टी के अजाफी जो इक़दामात हैं उनको अपनी लैब में लाना चाह रहे हैं। और इसके अलावा एयर फ्लो या एयर फिल्ट्रेशन की बजाय बायोसेफ्टी कैबिनेट में की जाए उसका मुतबादिल ये है। और छोटी लैब बेहतर है बहुत बड़े किसी कमरे से। और बुनियादी या बेहतर प्रैक्टिस या बेहतर हमारी जो लैब के काम है उसके लिए या PPE का इस्तेमाल, जिसमें बेहतर प्रैक्टिस में हम जैसे कहते हैं कि GMPPs हैं या गुड माइक्रोबायोलॉजिकल लैब प्रैक्टिसेस हैं और PPE का इस्तेमाल ज़्यादा अखराजात से इस्तेमाल करके ज़्यादा अखराजात से बचा जा सकता है और रिस्क पे भी काबू पाया जा सकता है। कुछ इजाफी या अहम इक़दामात लेके बासानी रिस्क पे काबू पाया जा सकता है, जैसे कि एक छोटी तरह से डिज़ाइन और मुनज़्ज़म तरीके से बनाई हुई लैब और गंदी हवा को निकालने के लिए या जो हमारी कंटेमिनेटेड जिसमें एरोसोल बने हुए हैं जरासीम के, उस हवा को निकालने के लिए एग्जॉस्ट फैन का इस्तेमाल। बहुत शुक्रिया, थैंक यू सो मच।
Yes, thank you very much, Zora, for this very good translation and so on. I would like to say a few words to finish. And first, thank you to all of you, to most of you, to have stayed to the end, even if you were late. Also for that, I want to apologize. I had real trouble to connect, and finally I could connect a little bit too late, and that's the reason. Then also a number of you ask questions, and there are some very interesting questions that raise very important topics. And so thank you for that. And we will have the opportunity to discuss that during next session. And then you might have more questions. If you have more questions, please ask them to PEPSA, but before this Friday, please. So thank you very much for your participation and attention, and hope to have you on board next time. Bye-bye.
The next session has been changed to November the 4th. Michelle, do you want to say something about that?
Yes, just thank you everyone again for attending. The next session has been changed because we had some conflict with the IFPA course, IFPA conference, and I know a lot of people who attend these sessions are also members of IFPA. So we will be having the next session on the 4th at same time, 5 p.m. We will be getting an email as usual, reminding you for that session time. And also I have put in the link for the evaluation in the chat box. So please remember to fill out the evaluations. Thank you everyone, and I'll see you on the next session.
I love it.